It's a very loud buzzing noise.
A very loud buzzing noise. How about now? We change the microphone. Can you hear me now? So hopefully that's the room microphone. People can hear me.
I don't think they can. Let's see. No response.
But they can see me. So this is the one that we've been using.
No one can hear you.
No one can hear me.
Excellent.
Great. How about now? Can people hear me now?
Yep.
Oh, that's good.
It's the one with the feedback. And speak up. Okay, so people can hear me now? The chat?
They're saying echoes.
Echo, echo, echo?
Yeah.
Is it still an echo?
Oh, they said all good now.
All good now.
It's good. Yeah.
Good. Okay. We're getting better at this. So, for those of you sitting in the class, how many of this is your second time you've actually been in here? Third? No. It's about every 5 classes. So, great, great. And as usual, I start off with questions. So before I launch into the PowerPoint lecture, first, while I'm asking for questions in the chat box, can people see the PowerPoint presentation? And at the same time, are there any questions from last time that the TAs can't answer or that you have for me? So last time what we did was finish up fluid properties, and then we launched into pressure measurement and fluid statics. And this is just a review. And remember, you have a handout from last time, and everything that I'm talking about in the slide presentation really is off of that handout. So we started with a differential cube of a fluid, completely submerged. And then instead of a three-dimensional analysis, we looked at a two-dimensional analysis. And the reason for doing that is that we oriented our XYZ axes such that the Z-axis was collinear with gravity. And therefore, X and Y have no other external forces acting or accelerations acting in them. So if we do a two-dimensional analysis, whatever we find for the X should be for the Y. And then what we did was, in this little cube, now 2D element, we assumed that pressure varied over the outside of this. And again, that represents the fact that we took this little cube and we removed it from the fluid, and these pressures acting on the outside is what's representing the rest of the fluid that's really out there. And we assumed that pressure was varying as you move through the system. So if we moved from the lower left hand or A to B, we had a change in pressure from PA to PB. Pressure is a scalar quantity. That means that it operates in the same in all directions at a point. When we integrate pressure over an area, we get a vector, and that's a force. And so what we did was apply Newton's first law to this: sum of forces in any direction is equal to 0. Not only do we have these pressure forces on the outside, but we have one body force. We call that the weight. And again, when we integrate the pressure distribution over any side, we get a force, and that is a vector. So when we did that, the next thing we did was, instead of looking at these pressures PA, PB, PC, and PT, we said, let's just say that we have at point A some pressure P, and then as we move in space, there's a pressure gradient. So if we move in the Z direction, we get a change in pressure due to the pressure gradient in the Z direction, dP, dZ. If we move in the X direction, we get a change in pressure, say from point A to point B, due to the pressure gradient dP, dZ. And the analogy we made last time is when you drive from here down to Florida in spring break, how the temperature increases as a function of the distance. There's a temperature gradient. So when we look at that and just put everything into this dimensionless pressure, not dimensionless, as this base pressure, capital P, and we substitute in the equations of Newton's first law in the x and the z direction, the first thing we find is dp dx is 0. It's a partial derivative because we assumed pressure varied in the x, y, and z. So pressure is a function of multiple variables. But this first one says that dp dx and therefore dp dy are 0. And what that means is if you move in a horizontal direction, when the only acceleration field is gravity, then you don't change pressure as long as you stay in the continuum, right? So if I have a glass of water and I move horizontally in a glass of water, I'm not changing pressure. But if I go outside of the glass of water into the air, obviously I've changed pressure, but I don't have a continuum anymore. So you have to have the continuum for continuum mechanics to operate. The next equation is the more important of the two, and that is that we do in fact have a pressure gradient in the z direction, and that pressure gradient, if we looked at a plot of, I'm going to put z on the vertical axis because physically it's measured in the vertical, but actually it should be on the horizontal because it's the independent variable, and we'll put pressure here. And so what this says is, if we move in the z direction, we're going to change pressure. So in essence, if we're moving in the z direction, as actually that's incorrect. That's not right. If we move in the z direction, because I have the axes changed, as I increase z, which is this direction, I'm increasing pressure. And the slope of this line would be 1 over gamma. So the inverse slope is gamma. So what does this physically mean? Again, no pressure gradient in the horizontal. And since all we have left is that pressure is a function of the z direction, now we can say that instead of a partial differential, we can just look at this as an ordinary differential. And I know you like an ordinary differential more than you like partial differentials. But ultimately, we're going to integrate this. This is a very simple equation, differential equation, that we can separate variables and integrate. And again, this is all on your handout. This equation 14 is the fundamental law of fluid statics. And basically it's saying that you have linear changes in pressures when you move through these fluids. What I do want to underscore is that, and as I stressed in the last lecture, I don't hold you to derivations, but you have to understand when you're violating them. So for example, I'm just going back onto this slide. So on this slide, we had assumptions that we have a continuum. The next one was that the density or the specific weight was constant. And we're going to relax that maybe at the end of this lecture or the next lecture, we'll talk about that. So for the distances we're moving over, the density or the specific weight, remember specific weight, gamma is equal to density times acceleration to gravity. So we're not changing gravity, we're not changing density. The other thing is that the only acceleration field is gravity. Can you have other acceleration fields? Absolutely. We'll get to that. So for example, if you're hauling, remember problem 1, you had this toxic hydrofracturing fluid in the tanker truck barreling down the road. And if it's just going at a constant velocity, that's a hydrostatic or fluid static situation. But once it takes a turn, now you've got accelerations in the horizontal direction in addition to gravity. You've changed the acceleration fields. So we're going to get to that. So right now, gravity is the only acceleration. And then we assumed that pressure was a function of x, y, and z components. But what we found was it's only a function of z, movement in the z direction. So those were the assumptions, and again, that's what you need to recognize, because when you violate them, obviously, these laws aren't going to work anymore, or they may not be as accurate as you hope them to be. So that's where we were just ending, and so now what we want to do is apply this. Okay, so on the right-hand side, remember, when you see that triangular symbol with the lines underneath it, that just means you have a fluid interface. There's two immiscible fluids on the either side of that longer horizontal line. It could be oil and vinegar, it could be air and water, it could be gasoline and water. They're just immiscible fluids. Okay, that's what that means. So, what we're going to look at, for example, we're down in the fluid here. So for example, imagine that above the interface you have air, below the interface it's a swimming pool. We have water. And we identified these 2 points, 1 and 2. At point 1, we're going to have some elevation coordinate, and at point 2, we're going to have another elevation coordinate. We have not established where the elevation datum is. In all of your problems for me, you will do that. So for example, you could say that at that interface, that's where I'm going to have my vertical coordinate axis datum. Z is equal to 0 what? 0 feet, 0 meters. It could be a local elevation datum. It could be an internationally recognized elevation datum. For example, the National Geodetic Vertical Datum. Okay? Or the North Atlantic Vertical Datum, NAVD 88 is what we use nowadays. So that's where we're setting Z is equal to 0. When we move vertically upwards to be consistent with the derivation, we're going into locations of Z increasing. 1 meter, 2 meter, 3 meter. When we started that data and go down into the fluid to points 1 and 2, that's in the negative Z direction. Minus 2 feet, minus 4 feet, minus 5 feet. Why? That's the way we did the derivation. Okay, we'll talk about changing that in a little later. So, if we take the equation we developed, dp to z is equal to minus gamma, separate variables, dp is equal to minus gamma dz, do an open integration. So we're going to integrate the change in pressure from point 1 to point 2. And when we do that, again, specific weight is a constant. It comes out of the integration. And we're going from P1 to P2, which is at Z1 to Z2. So we just perform that integration. So again, as you all know, the integration of dP is P, evaluated those two integrals. The integral of dz is just Z, evaluated at those two intervals. And so when we perform that integration, we would get P evaluated at P2 and P1 is P2 minus P1 minus gamma Z2 minus Z1. That's not so bad. And there's a lot of ways of rearranging this. You can group like variables. You can divide the whole thing by the specific weight. It doesn't change what it's saying. What it's saying is if you go from either 1 to 2 or 2 to 1, it doesn't really matter which way you're going. There's a change in pressure. Why? Because you had a change in elevation. The magnitude of that change in pressure has everything to do with the specific weight of the fluid and how far you went. And remember, in this coordinate axis system, as you look at this, both of these numbers, Z1 and Z2, are negative because of where we said Z was equal to 0. If you said Z was equal to 0 somewhere down at the bottom here, now Z2 is a positive number and Z1 is a positive number. But that's still true. Irrespective of where that datum is, delta Z is the same, right? And what dP dz is saying is that as you go down in the fluid, you're increasing pressure. So this is basically the pressure distribution. And if you recall, when we started out this talk, we want to know that. And one of the examples I showed you was the dam. On one side of the dam, you don't have water. On the other side of the dam, you do have water. We will take that pressure distribution and integrate it over the upstream side of the dam to get a force. Or any other fluid-solid surface interface you can think of. That's what we need to do to convert the pressure distribution into forces. So for this same problem, again, we just derived the equation at the beginning of this slide. That was on the last slide. And if you look at that equation, 2 pressures, specific weight, and 2 elevations, 5 variables, 1 equation. The only way to solve that equation is to either know 4 of those variables or have boundary conditions that dictate what some of those variables must be. But you have to have 4 out of 5, right? Otherwise you can't solve it. So we need to know 4 or 5. And again, those 4 or 5 will be either dictated or they're things that you can recognize. So for example, if this is air, remember, think of a swimming pool, and this is water. What pressure is above the fluid surface?
One atmosphere or 1 atmosphere.
1 atmosphere, atmospheric pressure. And atmospheric pressure in a local gauge datum is what? What do we set all of our local gauges to? 0. 0 psi, 0 Newton per meter squared, 0 Pascal. That's the local datum. Just like as far as the local datum, we can say that Z is equal to 0 right at the fluid surface interface. That's a local datum. So what you know is when you have atmospheric pressure, operating on top of a fluid surface, that's known as a free surface. I put that in capitals, at the interface. You could have atmospheric pressure somewhere in the continuum, and that's what you'll see. We're going to talk about that. But a free surface is a very special definition. Atmospheric pressure at the interface. And so again, we were talking about this equation up above, and that you have 5 variables. One way to get rid of 2 variables is in your problems, recognize if you have a free surface. If you have a free surface, you can put your elevation datum there and you know the pressure. Now you've got 2 variables out of the way right there. You would know the pressure of the free surface, and you would know the elevation of the free surface. Okay, so again, the free surface is where we have atmospheric pressure at the interface. It's convenient to set that elevation datum also at that surface. And again, you've knocked off 2 of the variables. So, first example for today. We've got, move this, basically the same situation, only the question is, what's the pressure 3 meters below the water surface in a lake? So the question would focus on this. What's the pressure here? The only equation we have right now is the one we just integrated. P2 minus P1 is equal to minus gamma Z1 minus Z2. However, in this, in this problem, What is that telling you as far as the 5 variables? Specific weight, right? So you know the specific weight. Now, you know that density and specific weight are temperature varying. No temperature is given in this problem. My guidance to you in the past, and will continue to be, if in this course a temperature is not given, assume it is at room temperature. 7 degrees Fahrenheit, 20 degrees C. When you leave here, it is incumbent upon you to know the temperature range of the systems you're looking at. So if you're talking about flow in pipes, water flow in pipes underground, that's probably going to be at the average annual ambient air temperature, wherever you are. Okay, so in this course, either the temperature is going to be given, and if it's not, room temperature. So again, that allows you to know the specific weight. The other one is this is basically telling you not only, for example, Z2, but it's also telling you delta Z. They're one and the same. And so if you identify this surface, so let's look at this right here. This is a lake. It's on the surface of the earth. Is that a free surface? Sure. Atmospheric pressure above it. And so you know that you have atmospheric pressure, and again, in a gauge pressure datum, atmospheric pressure is 0. You set your elevation datum here, and that means you know Z1. You already have Z2, but you also have Z2 in terms of that datum. Z2 would be minus 3 meters. Remember, Z increases vertically upwards. We're looking 3 meters below the surface. We know the specific weight. We know P1, Z1, Z2. The only thing left in that equation is P2 of those 5 variables. So we let the elevation be at the water surface. We assume that. Can you put the elevation datum anywhere? Absolutely. It could be 500 feet above, 10,000 feet below. It's incumbent that you can actually figure out the 2 elevations at those points. So don't make the elevation datum part of the unknowns. So again, since we set the elevation datum at the water surface, and we know that the water surface is a free surface, we know Z1 and we know P1. And again, what we're trying to do is solve P2 minus P1 is equal to minus gamma Z2 minus Z1. So again, we know everything in this equation except P2. P1 we can bring to the other side, but we also know that it's 0. And again, from this elevation datum and from the statement of the problem, we want to know the pressure 3 meters below the fluid surface. We know that the elevation datum, Z is equal to 0 at the fluid surface, so Z2, the point of interest, is minus 3 meters. And again, since temperature wasn't given, we're going to assume that we have room temperature. Don't we wish that all the ponds and lakes were at room temperature? And when we go to the back of the fluid mechanics textbook, you can see that the specific weight for water at 20 degrees C is 9,790 Newton per meter cubed. So again, we're trying to solve this equation. That's the one I just put on the previous slide. And again, we can rearrange it. So we just brought P1 over to the other side. We're interested in calculating P2. Could we have called the point at the surface P2 and the point at the bottom P1? Absolutely. You're going to get the same answer. It's just got things rearranged differently, but you'll get the same answer. So it doesn't matter which point you call 1 and 2. You have the same information available to all ways you define the problem. So once we've rearranged the equation to solve for P2, now we can just plug, chug, and go. We put in the specific weight, we put in Z2 and Z1, and we put in P1. And then when we crunch that number, we get 29,370 Newton per meter squared, Newton per meter squared. That wasn't so bad. Baby steps. should be pretty straightforward. Are there any questions on that before I move on? Today I'm doing mostly examples. Oh, and speaking of which, yesterday I posted that we were going to have the first of the optional homework review sessions. So if you have any questions about the homework problems on the syllabus from the book that I do not collect, I'll be submitting a Zoom invitation this afternoon. I know a bunch of you are going to say, I have class then. Again, this is optional. It doesn't prevent you from asking me questions outside of this. I will have other of these review sessions. I try to have 2 before every exam. I believe our first exam is the first week in October, so that's not too far away. And the other one I'll try to have at a different time on a different day, just so we can get as many people as possible. So again, this is optional. If no one signs in tonight, it's not going to break my heart, believe me. Okay, here's the second example for today. Many of you, if you ever listen to the weather on either the television or on the radio, they'll talk about barometric pressure. So remember, when we talked about pressure measurement, we indicated that there are certain devices that measure absolute pressure in the absolute pressure measurement datum, and other gauges that only measure gauge or local pressure. And the difference is that anything that measures gauge pressure, that gauge is zeroed on local atmospheric pressure. Whereas anything that measures absolute pressure, somewhere in the device has the closest thing to a perfect vacuum we can create. So what you see is this container filled with mercury, that's here, and you have an open bottom tube that's closed at the top, and a column of mercury standing up in it. When these are made, we try to create a vacuum up there. But what's really up there is the vapor pressure of mercury, which is incredibly small. I believe it's in your book, so you can certainly test this. So basically in this question, we're posing it as, if you have a reading of 760 millimeters of mercury, what's the barometric pressure? And the answer actually is it's that 760 millimeters of mercury, only that's representing pressure as a column of fluid. So you can either represent pressure as a column of fluid by bringing specific weight over to the left-hand side, or you can represent pressure as a pressure. So we're asking for the atmospheric pressure in terms of pressure. So what we have is this column of fluid, and the first thing you ask is, from the column of fluid into the container of the same fluid, mercury, first question, do you have a continuum? Can you draw a path that connects all the fluid? Absolutely. So within the mercury, we can apply continuum mechanics, which means we can apply this equation that we've derived. And again, it seems so obvious that there's a continuum. When you leave here in practice, it's not always that obvious. Why? Because all the pipes are underground, and you don't know if some of the pipes are filled with air or not, because you have cavitation or some way of air getting into the system, backflow. So again, it seems obvious in a lot of the cases we look here. When you leave here, that's the challenge. You never really know unless you can see the complete system. So again, the vacuum pressure inside the barometer, that's at the very top in the column, we're going to assume is the perfect vacuum. We're going to let the elevation datum be at the surface of the mercury in the container. That's where we're going to say Z is equal to 0. And we also made that our elevation datum because I'm just going to go back. So this is where we're saying Z is equal to 0. And again, you have atmospheric pressure all outside of this, and this is the interface between the air and the mercury. That is a free surface. This is not a free surface. You do not have atmospheric pressure there. Out here where the blue arrow is, that is a free surface. So again, where I see a free surface, I very commonly say, well, I know the pressure, but I'm also going to set my elevation datum there. Do you have to? No. Again, you can set your elevation anywhere, but typically you set it where you know some measurements to it. So we're going to say point 1 is going to be that mercury surface exposed to the atmosphere, and point 2 is going to be the mercury surface inside the barometer at the very top of the barometer. So again, point 1 is at that interface, and point 2 is at the other interface. The difference between those two interfaces is that this one is at atmospheric pressure, and the other one again is at a perfect vacuum. And we set our elevation datum again at that free surface of Mercury. From the back of your book, the specific gravity of Mercury is 13.55. No temperature was given, so the specific weight of water is, again, just like the last problem, 9790 newton per meter cubed. And you ask, well, why are you using water? Well, I don't have the specific weight of mercury, and I need the specific weight of mercury. And you know that specific weight of any substance is equal to specific gravity of the substance times the specific weight of water. Right? And so we'll calculate that out, and you'll see that the specific weight of mercury is 133,000 newton per meter cubed. And again, I just rounded to 3 digits. And at point 2, we know what the pressure is. At point 1, we know what the pressure is. It's atmospheric, but that's 0 in a gauge sense. I want to know the pressure at 1 in an absolute pressure measurement data. So P1 is actually the unknown. It's the real absolute atmospheric pressure, and Z1 is 0, Z2 is going to be 0.76 meters, 760 millimeters. So again, if we look at our equation that we're solving, and this will probably be on the next slide, P2 minus P1 is minus gamma Z2 minus Z1. And this is good for any continuum of a static fluid. Our static fluid continuum is mercury. P2 is the perfect vacuum. Z1 is 0, and Z2 is the 0.76 millimeters. So the only thing we don't know in this equation is P1, the absolute pressure of the atmosphere. So again, this is the same equation I had on the previous slide. I'm just rearranging it now to solve for P1. In the last example, we solved for P2. And again, if you had changed the numbers around, if P1 was up in the manometer and P2 is at the free surface, you're going to get the same answer. It doesn't matter which point you call 1 and 2. So now we can insert everything we know, because the only unknown we had was P1. P2 is the pure vacuum inside the barometer. Gamma is the specific weight of mercury, which we calculated before. And then you can see the elevations, Z2 and Z1. Z2 is at the top of the barometer. It's a positive 7.6 meters because the elevation datum, where Z is equal to 0, was down below at the free surface of the mercury. And so that gives us an absolute atmospheric pressure of 101,000 newton meter per squared. And notice, you identify that pressure datum. This is an absolute pressure. So the 760 millimeters, again, is representing a pressure as a column of fluid, which is fine. The 101,000 newton meter per square absolute is representing the pressure as a pressure with the dimensions of force per length squared. So that's your local atmospheric pressure question.
In your second line, is that supposed to be minus the specific weight?
Okay, so look, you mean right here?
Yeah.
So the question was, should that be minus? So what I did was I isolated P1. So I brought P1 over to this side, and this one over to that side, and that's how I got P1 and the gamma Z2 minus Z1 to be positive. I like questions like that. Yeah.
Then why is the 133,000 negative?
Why is this negative?
Yeah.
Probably because I screwed up. That's a good point. That should be a positive. Otherwise, I get a negative atmospheric pressure. Yeah. So 1 point for me, 1 point for you. And commonly, again, we can have devices, so we'll use pressure transducers, for example, to measure wave height. And when we throw that pressure transducer into the ocean, we'll tie it to a cinder block, throw it in the ocean, and then we'll be measuring the water level over it. Since it's not vented, the pressure transducer is not vented, we have absolute pressure being measured. So we need another transducer above the ground measuring the atmospheric pressure. When we subtract the two, we get the wave height, the water height, which is the class before us, coastal measurements. So, right now we have this equation. And that negative sign, as we just saw in the questions that were being asked, can lead to a lot of furrowed eyebrows. And it all results from the fact that we assumed that z was positive upwards. So what if we went through the entire derivation, and instead of using x, y, z, we used x, y, h. And now h was positive downwards. That's the only difference. H is positive downwards. And if you had done that, what you would have found is the exact same equations in the horizontal. dp dx is equal to dp dy is equal to 0. Because again, gravity is only aligned with the z and now the h-axis. And if you had gone through that, what you would find is now that instead of dp dz is equal to minus gamma, dp dh is equal to gamma. And again, if this is a free surface, now as you go down into the fluid, the pressure and the h-axis are both increasing as you move downward. With the z-axis, z increases up as pressure increases going down. And that's what gives you that negative sign there. And so very simply, let me see. Before we had this equation that we integrated with respect to z. Now when we integrate it with respect to h, we just lose the negative sign on the right-hand side. That's the only difference. However, what's really convenient is, just like the last problem, the first problem of the lake, if you have a free surface, and you integrate this, if you want to calculate the pressure somewhere below a free surface, this equation basically comes down to the pressure anywhere below a free surface is just the specific weight of the fluid times the distance from the free surface down to the point you're looking at. So if you look at the first problem we did where we wanted to know the pressure 3 meters below the fluid surface, you would have just done that. No integration, no using the big equation. By recognizing you have a free surface, you're using these equations and just recognizing that at one location, pressure and elevation are both 0. So it really uncomplicates this. Underscore free surface. Not all problems have a free surface. Okay. So that's what we just said. So it's possible to have problems, and we're going to do one next, where you have gases and liquids in the same problem. For example, air over water. If you look at the density of air, and these are right from the back of your book, at 20 degrees C, density of air is almost 3 orders of magnitude smaller than the density of water. And this is common between liquids and gases. And so if you did have a problem where you had a gas over liquid, what we would draw as far as a pressure distribution, so I'm drawing pressure out this way versus distance down from the top. Let's say we had this container under some pressure. So if this is a pressure gauge right here, we would have some pressure in the gas at the very bottom of that gauge. And because of that density or specific gravity distance difference between liquids and gases, we would basically say that there is no pressure change in this finite difference in the gas from the top of the gas to the bottom. Why? Because this specific weight of the gas is so small, there's almost imperceptible past 3 place digits, imperceptible change in the pressure. So if you measure the atmospheric pressure at the top of this room, 20 feet off the ground, and the atmospheric pressure here, and you only had a gauge that read to 4 place accuracy, you wouldn't be able to see the change in the pressure. You have to go over great distances in the gas. Once we hit the liquid, then we would see a change in pressure. Okay? Everybody understand that? However, if you have one liquid over another, yes, you're going to have pressure increases in both of those, and they're going to be at different rates as the difference in the specific weights. And we're going to be doing all these problems. I'm just trying to introduce these concepts to you. So we don't always have fluid continuums. We use continuum mechanics in them. When we have gases versus liquids, typically we assume that there's no real pressure change when you move vertically through finite difference of the gas. Obviously, as you move through our atmosphere through miles, yes, you do get changes. Most of our engineering problems are in systems that are that large. So we've kind of beaten this dead horse with a dead stick. So here is the problem I was just talking about. We have a closed container. This closed container has a pressure gauge at the top, and that pressure gauge is reading -2 psi. What would happen if I poked a hole in the side of this container? What would happen? Air would be sucked in, right? And you'll learn about why later, but basically you have something at higher pressure outside than inside. And that pressure gradient is an energy gradient that drives flow. We're getting to that. So that's why this is a closed container. We have a pressure here that we're basically going to say is uniform of -2 psi. And then once we get to the water, then this is going to be increasing pressure. So 0 psi, remember pressure is being measured on the horizontal axis. So 0 psi is here. So we would start at the surface of the water at -2 psi, and then as we move into the fluid, the water in this case, we're getting higher and higher pressures. Somewhere between the top of the fluid, the water in this case, where you have -2 psi, and the bottom, you probably have a 0 pressure somewhere. We'll see. So the question is, if the pressure in the air is 2 psi, we know the pressure at the interface is also -2 psi. And so what we're after is, what's the pressure on the bottom of the container? So we're going to let point 1 be at the interface between the two. Is that a free surface? What's the litmus test for free surface? Do you have atmospheric pressure there? 0 gauge pressure or 101,000 Newton per meter squared absolute? Do you have atmospheric pressure there? No, it's not a free surface. It's just an interface. Got it? So that P equal gamma H stuff I just told you, you can't use because that's only good for a free surface. So that's going to be point 1. And if we want to know the pressure at the bottom of the tank, we're going to locate point 2 down there. And again, if you call point 2 at the interface and point 1 at the bottom, that will not change the answer. The other thing we're going to do is, at the interface, we're going to say the elevation datum, H is equal to 0 meters in this case. Always put units next to your numbers. H is going to be equal to 0 meters right at the surface. So if that's true, what's H2? Seven or minus 7? Which way does the h-axis increase? Down. It increases down. So what's h2? 7 meters. Very good.
We're using feet or meters?
Is this in feet? Oops. Feet. Sorry. Thanks. I wasn't looking. And so this P1, Z1, or H1, would be equal to 0 feet. And again, we would have P1 plus gamma H is equal to P2. So we started here. That's where we just arrived. And so this would say that P2 so all I did was group like subscripts. I brought gamma H2 to the left-hand side. It was positive on the right, becomes negative on the left. And I brought P1 to the right-hand side. That was negative on the left, becomes positive on the right. So that's true. And you know H1 is equal to 0. And if we now rearrange this, that P2 is equal to P1 plus gamma H2, you get the form that's up here. So I always start at the same place, but in time you'll learn that you can just probably start right here because you recognize that by setting the elevation datum right at the free surface, you get rid of one term. So if we wanted to calculate the pressure at the bottom at point 2, that's what this equation says, we would start at the pressure at the surface, minus 2 psi. And then we would calculate the change in pressure as we move through the water. That's plus gamma H2. Why is it plus? What that's saying is as you move down into the liquid, into the water in this case, you're increasing pressure, right? And that makes sense to you. And so the pressure at the top, minus 2 psi, as you move down through the fluid, I'm just going back to the previous page. Here we go. We had a minus 2 psi at the surface, and once we move from the surface, we're increasing pressure to something at the bottom. So I know it's a little complicated now, but you can see P1 is the minus 2 psi, and then gamma H is 62.4 pound per cubic foot. That's the specific weight of water. H2 is 7 feet, and then the conversion from pounds per square foot to pound per square inch is 144 inches squared per foot squared. And that means the pressure at the bottom is 1.03 psi. The change in pressure from the surface to the bottom is 3.03 psi. And so again, we went from minus 2 psi down to a positive 1.03 psi. So again, if you have minus 2 at the surface of the water and 1.03 at the bottom, somewhere between the two is 0. That's not a free surface because it's not an interface. It's just in the water. Is that possible? Of course it is. Question?
I just have a quick question. So you said in the beginning of the problem that pressure was at the gauge was negative 2 psi. There's no pressure change between where point 1 is and the gauge.
So if you have a gas and you have a liquid,
Yep.
because of the very small relative density of the gas to the liquid, the change in the vertical air is negligible.
Okay.
And I challenge each and every one of you to convince yourself of that. Make that distance 2 feet from the top of the container to the interface and calculate the change in pressure through the air. It may be 5 or 6 zeros and then a number.
Okay.
You're not going to see it. So we're on the same example, and I know I've got 1 minute left. The same thing that I just indicated, we could calculate the exact location where you have 0 pressure. So in this case, all we would say is, what's the distance down to a location where we have P equal to 0? In the last problem, we knew an elevation and we wanted to know the pressure. In this problem, we know the pressure, we want to know the elevation, the distance. It's the exact same solution setup. It's just who changed was the variable we're after. So we would start at the same place. We know the pressure at point 3. And we would just rearrange this equation to calculate the depth to which we would find that. And again, I will post this. I know we're almost out of time, but basically, the depth of water was 7 feet in this tank, and at 4.6 feet, that's where you have 0 pressure in the water. So the pressure above 4.6 feet to the interface is negative. The pressure below that is positive. Has anybody ever used a straw? Of course. Let's say you drew water up in the straw and put your thumb on the top of it. That straw continues right down into the fluid. So you drew the water level and you put your big fat thumb over this. First thing is, do you have a continuum between the fluid and what's in the straw? Of course. And so if this is 0 along the free surface outside here, dP dx is 0. If I move from this location to this location, I'm going horizontally, even though physically to stay in the continuum, I went down and up into the straw, but I went through a continuum. The pressure at dP dx has to be the same. There's no change in pressure if you move in the x. Okay? So this would be the exact analysis of what's happening in the tank. And you've seen this before, I know it. You just never applied math to it. So, any questions? Labs due Friday, is that true, TAs? I probably will post a homework so you don't forget about me on this stuff. Any chat box questions?